Hello everyone, let us continue with what we have been doing since last few classes. We have been discussing influence line diagrams and moving loads. What we have done so far, let us quickly review that. There are majorly three problems we may encounter. One is influence line diagram is essentially required to understand to deal with loads that are not at rest condition. The loads are moving on the structure for trains, on bridges, vehicles, on flyovers and so on. Now, there are mainly three problems. One is the drawing of influence line diagram. So that is essentially how if a unit load moves on the structure, then how the internal forces and support reaction changes with the location of the unit load. So that's what that change, the graphical representation of that change is the influence line diagram. Okay, so one aspect is the drawing the influence line diagram for the given problem, for the given structure. Now, once the influence line diagram is drawn, then the next is, suppose you have a load that could be a concentrated load, that could be uniformly distributed load, a several concentrated load moving, a train of concentrated load. Then the next problem is, for a given location of that externally applied load, what would be the internal forces? That is also very straightforward. What we need to do is, we know the location of the load, and corresponding value we can get from the influence line diagram, and that value will give us what would be the internal forces. We have seen that in the last class. And then the third problem is, as the load changes its position, then there will be a critical position for which the internal forces or the support reactions will be maximum. What we need to find out, what would be that critical position for which the structure is subjected to more, the internal forces in the structure is maximum. We have discussed that in the case of uniformly distributed load in the last class. What we do now today is, if it is not uniformly distributed load, if the load is not cannot be idealized as uniformly distributed load, if it is a train of concentrated load moving on the structure, then what could be the critical location for which the internal forces will be maximum in the beam. But so today's topic is the influence line diagram in a train of concentrated loads. But before we do that, let us quickly see what is the problem, describe the problem first. Again, let us consider the same bridge that we started with our discussion of in this week. Now, suppose this is a vehicle is moving on this bridge like this. Now, if you see, there are, say, here we have six wheels in this vehicle. Okay. Now, suppose this is a given location of the vehicle. Now, whatever load on the vehicle, that the self weight of the vehicle, that will be transferred to the bridge through these wheels. Okay. Now, as the load moves, the relative position of the wheel remains same. They are not changing. They won't change. Okay. Now the total load will be transferred to the bridge through these wheels, and that each wheel will apply the concentrated load on this structure. So, this can be idealized as a concentrated load on this structure. So, these are wheel position. Now, this load, this is a train of concentrated load. Now, this train of concentrated load is moving on this structure, but as they move, the relative position of between these loads, they are same. Okay. So, what we want to do now today is, as this load moves, the internal forces in this member change, and what would be the critical location of this load for which the internal forces will be maximum. We have done it for uniformly distributed load. This is we have already proved in the last week that if the load is uniformly distributed load and subjected on a simply supported beam, because this mid structure can be idealized as a simply supported beam. So, if a uniformly distributed load is applied on a simply supported beam, then this is the influence line diagram for bending moment. Then for and suppose C is the location of the at any given location at which we want to determine what would be the bending moment. Now, the bending moment at C will be maximum if the load is placed in such a way that A1 by A is equal to B1 by B, where A and B are the point C divides the beam AB by in A by B ratio, and the same point C divides the load in A1 by B1 ratio. So, if A B and A1 BI, they satisfy certain criteria, and this is the criteria. If they satisfy that, then the bending moment at C will be maximum. Now, what is exactly this criteria? If you see A1 by, if you multiply both sides by Q, then Q into A1 will be essentially the load on this part. Total load will be Q into D, and Q into A1 will be the externally this uniformly total load on AC, and similarly Q into B1 will be total load on CB. Now, Q into A1 by A is essentially the average load on AC, and Q into B1 by B is the average load on CB. So, what it says, the criteria says that you place the uniformly distributed load in such a way that the average load on the left side of the beam equal to the average load on the right side of the beam, then that is the critical position, and for that position you get the maximum bending moment at C. And what would be the bending moment at C? This is the influence line diagram. So, bending moment at C will be area of this this area will be the bending moment diagram. We know that this value is AB by L. So, we can determine this value and this value and get this area. So, this area will be give you the bending moment at C. This is the critical location for uniformly distributed load. Now, the same thing, same exercise we are going to do it for train of concentrated load. Now, suppose this is the same beam AB, simply supported beam, and this beam is subjected to and C suppose is the center point of the mid span of the beam, and so if the total length is L, so AC is L by 2 and CB is L by 2. Okay. Now, suppose this is subjected to a train of concentrated load, and these distances between two consecutive concentrated loads are same, not same, they remain same, they do not change as the load moves on AB. Okay. Their distances, this distance may be different, but if you take any two consecutive forces and their distance will remain constant as the load moves on AB. Okay. Now, suppose these loads are suppose we take any point D at which we want to find out what would be the bending moment. So, we need to find we are going to find out what would be the critical location of this concentrated load, the load system, for which the bending moment at D will be maximum. D could be any arbitrary location between A and B. Okay. Now, suppose this point D is at a distance x from A. Okay. Now, what is and naturally the total length is L. So, this length become L minus x. Okay. Now, suppose these loads are, suppose we have total n such loads. In this load system we have n concentrated loads, and suppose the loads are denoted as P1, P2, P3, P4 and so on, and then Pi minus 1, Pi plus 1 and up to Pn. So, total we have n concentrated load. Okay. Now, next is, so what would be the resultant of this n concentrated load? They all are vertically downward, they are all parallel load, but their line of actions are different. So, total result, the resultant of this n concentrated load will be their summation. So, resultant will be summation of Pi, where I summation over I is equal to 1 to n. So, total the sum of all this load will be the resultant of this load. Now, suppose this resultant of the entire of n concentrated loads, that resultant acts at a point E, means the line of action of the resultant suppose is this, and that line of action intersect the beam AB at point E. Okay. And now suppose this point E, the line of action of the resultant is at a distance d from point D at which we want to determine the bending moment. Okay. Now, now you see this is the resultant of total load, okay, total load acting on AB. Now, up to the left side of the beam, left side of point D, how many loads we have? We have P1, P2 to Pi minus 1. Suppose these are the loads acting on AB, but on the left side of on the left side of D. And resultant of these loads are, suppose again summation of all this, resultant of this load is Pk, where k varies from 1 to I minus 1, because I minus 1 P1 to Pi minus 1 loads, concentrated load forces are acting on one side of the point D. Okay. Okay. Now, again suppose this line of action of this resultant is F. So, E is the line of action of the resultant of the entire load, and F is the line of action, or F is the point at which the resultant of the load P1 to Pi minus 1 acts, and P1 to Pi minus 1 are the forces which are on AB, but one side, on the left side of D. Okay. Now, and suppose this distance is small e. So, capital small d is the distance from D, distance of the resultant of entire load, and small e is the distance of the resultant of the loads which are on the left side of capital D. Okay. Now, so now come here, let us see what is the critical position. Okay. Now, this is the same figure just now we discussed. Okay. Now, let us first draw the, now what we want to do is, as I said, we want to find out what would be the location of this entire load system for which the bending moment at point D is maximum. Okay. Now, let us draw the free body diagram of the entire system. Now, if we draw the free body diagram, so this will be By and this will be Ay. This will be Ay. Okay. There is no horizontal force, so Ax will be anyway 0. Ax will be 0. Okay. Now, let us take moment about, we need to find out what is the reaction at Ay. Let us take moment about B. If we take moment about B, so summation of moment about B is equal to 0. Now, what are the forces that will contribute? Ay will contribute, and A contribution of Ay will be clockwise. So, it will be Ay into L positive. Now, you see all these By will not contribute because we are taking moment about B. All these forces will contribute, all the vertical forces or concentrated load you can see, they will contribute. Now, taking moment of individual forces is same as taking moment of their resultant, but the resultant of the entire forces. So, instead of taking moment of the individual forces, what we do is we take the moment of their resultant. What is the resultant of all the forces? Resultant of all the forces is, this is the resultant. This is the resultant of all the forces. Okay. And what is the, at what point it acts? It acts at point E. And what is the distance of E from B? This distance is L minus x, and then this distance is D. So, this is L minus x plus D. So, and all these forces will act anti-clockwise moment. So, this is minus resultant is summation over I is equal to 1 to n Pi. This is the total resultant, and it is acting at a distance L minus x plus D. So, Ay will be L minus x plus D by L into summation of Pi, I is equal to 1 to n. So, this is the support reaction at A. Okay. Now, Once we know the support reaction, let us find out what is the we want to determine what is the condition for which moment at D is maximum. So, let us find out what is the moment at D. So, in order to do that, let us take AD and draw the free body diagram of AD. Now, what is the free body diagram of AD? At A we have AY, the value of AY is this is A and this is D. At D we have shear force Vd and then moment Md, and then we have all these between A to D, all the concentrated forces from Pi to P1 to Pi minus 1. Okay. Now, we want to take moment about D. So, one way is we take moment of each individual forces, or instead of that take the moment of their resultant. Their resultant is this, So, what we do is we take the moment of their resultant from D, and the resultant acts, this is the resultant, and this value is summation of k Pk, where k is equal to 1 to I minus 1, okay, I minus 1. Now, take moment about D. If we take Md is equal to 0, then what expression what we have? Let us determine that. We have Ay into this distance, okay. Ay is, and this distance is x, we know this distance is x, okay, and this distance is E, So, determine the forces, summation of Md is equal to 0. What we have? If Ay will contribute Ay into x, and then minus summation over k Pk, k is equal to 1 to I minus 1, this is the total load, okay, into E, and then minus Md, that is equal to 0. And if we do that, and we get Md is equal to, the expression for Md is equal to Ay already we obtained. If we substitute that value, this will be L minus x plus D into x divided by L summation of Pi, I is equal to 1 to n, minus this, minus E into summation of k Pk, k is equal to 1 to I minus 1. This is the expression for Md. Okay. Now, our condition is, as for maximum Md, dMd dx has to be 0. If we do that, this part will anyway 0, and if we do that, then what we get, this will give us x is equal to L by 2 plus D by 2. This is very important. So, if x is equal to L by 2 plus D by 2, then Md is maximum. Now, what is x is equal to L by 2 and D by 2? Let us see in this case. What is, you see, x is equal to L by 2 means at point C, okay, this x, and then D by 2 means D is the distance of D from the resultant of the entire load. So, this distance, so CD, if this distance becomes D by 2, this distance becomes D by 2, then the moment at D will be maximum. Okay. So, this says that the total load should be placed in such a way that D should be located at a distance D by 2 from the from the mid span. C is the mid span and D is the point at which we want to determine the bending moment. If this distance is d by 2, then the bending moment at D will be maximum, and D is the distance of the resultant of the entire load from point D. Okay. So, this is the condition. The condition will be clear if we just quickly do one example. Take this example. This example is again the same problem where we have okay. You see, this is a vehicle moving on this bridge, and there are two wheels which is 1 meter distance apart, and the total load of this vehicle is 25 kilonewton, and then the wheels are placed in such a way that this wheel will apply concentrated load of 10 kilonewton, and this will apply concentrated load of 15 kilonewton, and this wheel moves this vehicle as this vehicle moves. These two load also moves on BC, okay, and this is moving in this direction, and the first is 10 kilonewton, which is followed by 15 kilonewton load at a distance 1 meter. So, what we need to find out, consider any point E at a distance 2.5 meter from B, what we need to find out what would be the position of this wheel for maximum shear force and maximum bending moment at E. So, let us try this problem. So, quickly, it is a simply supported beam, and this length is total length is 10 meter, okay, and then we have a point E which is 2.5 meter distance, point E which is 2.5 meter distance. Okay. We want to find out what is the, let us first do it for maximum bending moment. Now, what is the influence line diagram for bending moment? Influence line diagram will be, this is the IL for ME, okay, influence line diagram for ME. This is B, this is C, this is C, this is B, this is C. And what is this value? If we know that if it is A, this is B, then this distance will be AB by L. Here A is equal to 2.5, B is equal to 7.5, and then L is equal to 10 meter, and then this value becomes 2.5 A into B by L is 10, this is 1.875, this value is 1.875, okay, and this distance is 2.5 meter. This is 2.5 meter and this is 10 meter, this is 7.5 meter, 7.5 meter. Okay. Now, what is the load we have? The load we have first is 10 kilonewton, and then this is 15 kilonewton, right? This is 15 kilonewton, and this distance is 1 meter. This is 1 meter. Okay. Suppose this is the resultant of the load. This is the resultant of the load R. Okay. Now, let us find out what is the value of R. What is this distance? At what point this R acts? Suppose what is this distance? What is this distance? Now, if we take suppose this is small a, B, C. Okay. If we take moment from A, then we have summation of M A is equal to 0. What are the forces will contribute? 15 will contribute, that is 15 into 1, it is clockwise, minus R into, say this distance is Z, R into Z, this is equal to 0, and R is 25. So, Z becomes 15 by 25 meter. So, this become 0. Z become 0.6 meter. Okay. This become Z 0.6 meter. So, this is 0.6 and therefore, this becomes 0.4 meter. Okay. So, this is 0.6 and this is 0.4 meter. Okay. Now, what was the condition? Condition is that we need to place the load in such a way that that resultant of R should be at a distance d by 2 from E. Okay. And what is then what would be the position of this load if this point is E, if this point is E, let us apply this load. This is the position at which we want to determine the this is the position E. Okay. And then the resultant acts somewhere here. This is the resultant of the load, this is the R, which is the resultant of the load, and then this is 15 kilonewton load, and this is 10 kilonewton load, Okay. And this distance is 0.4. This distance is 0.4. So, d is equal to 0.4. So, if this distance is 0.4, E has to be, E should be the midpoint of this and this. Okay. So, this distance will be then, this distance will be 0.2 and similarly, this distance will be 0.2. Okay. So, if this distance is 0.2, draw the corresponding line here and again draw the corresponding line here, and this distance is we know that this distance is 0.2 and then this distance will be 0.8. Total distance between two load is 1 meter. Okay. Now, next is what we have to find out, what would be the moment. Moment will be 10 kilonewton multiplied by this distance and then 15 kilonewton multiplied by this distance. And if you find out these distances, these values will be, I leave it to you, this value will be 1.275, because we know all these distance, this is 2.5 meter, this is 0.8 meter and this is 0.2, and similarly this value will be 1.825. Okay. So, bending moment ME max rather will be 10 into 1.275 plus 15 into 1.875 meter, and this will be 40.125 kilonewton meter. This is ME max. All this calculation, please you do it yourself and check whether you are getting these values or not. Okay. This is for maximum bending moment. Now, just quickly we check what would be the position for maximum shear force. If this is and this point is E, this is 2.5 meter and this is 7.5 meter. We know what is the influence line diagram for shear force. Influence line diagram for shear force is this. This value will be 0.25 or minus 0.25 and this is 0.75. This is B, C, this value is E. Okay. Now, we need to find out what would be the, this is positive, this is positive, this is negative. Now, the first case, if the load positions are like this, load first 10 kilonewton load is this is 10 kilonewton load, and then after 1 meter we have 15 kilonewton load and this distance is 1 meter, then what happen? Your shear force will be 10 kilonewton into this plus 15 into this. In this case both are positive. So, you get maximum positive shear. Now, if the load slightly moves in this direction and takes a position like this, here it is 15 kilonewton load, 15 kilonewton, and here it is 10 kilonewton load, 10 kilonewton load. In this case what happens? So, your shear force will be 15 into this distance plus 10 into this distance. So, your shear force will be maximum negative shear. So, for V maximum positive will be this into this. This value will be 0.65 and this value is 0.15. You can check it by applying similar triangle. So, V max will be 0.75 into 10. So, 10 into 0.75 plus 0.65 into 15. This is 17.25 kilonewton, and similarly V negative max, this will be 0.25 minus 0.25 into 15, and this is minus 0.15 minus 0.15 into 10, and this becomes minus 5.25 kilonewton. Okay. So, this is for maximum positive shear, this is negative shear. Okay. So, this will be the position of the shear force. Okay. Now, it is a small very simple demonstration of the concept that we have learned today. Again, as I have been telling in almost all classes that this is not the all in whole. You have to really see some more examples from the book to understand the concept and apply it in a better way for different kinds of problem. Okay. Thank you very much. Now, we stop here. In the next class what we do is you see almost whatever discussion we have so far is, in order to draw the influence line diagram, we actually need to solve the problem. We need to find out the support reactions, get the expression for moment, shear, and draw the and essentially influence line diagrams are the graphical representation of those expressions. But there is a very interesting way to find out influence line diagram without actually solving the problem, and that is very much important for indeterminate structure, because solving indeterminate structure itself is is not a very straightforward thing like determinate structure. So, what we learn next class is Muller-Breslau principle, which tells you that if we have some understanding about the deflected shape of the structure, then based on that we can draw the influence line diagram. Okay. With this, thank you very much. See you next class.